All right, sorry about that. So this is going to be 0.001. So here we could see that we're going to have the same situation as before, but here the numerator and denominator both have negative signs, so this is actually going to be a positive value in the end. So we're going to have a positive value, and this is again going to be increasing in the amount. So it's going to be going to plus infinity. You could check this out numerically. You could pick test points and make a table, and you will see that the values are going to be increasing and tending to the positive side. So here we could say that the limit as x goes to 3 from the left side of 2 minus 5x, x minus 3 is equal to plus infinity. All right. Okay, cool. So let's do maybe one more example and we call it a day. Okay, so let's say we have the following function. F of x equals x squared minus 4x plus 3 all divided by x squared minus 1. And we are trying to look for the limit as x goes to 1 of f of x, so that's number 1, 2, limit as x goes to minus 1 from the left side of f of x, and 3, limit as x goes to minus 1 from the right side of f of x. Now here we have a rational function. If you notice, for the first one, so if we begin to work on the first one, limit as x goes to 1 of f of x, if you plug in 1, you're going to get undefined in the denominator. So that means that x equals 1 is a very class asymptote for this function. So you have to be a little more careful. What I always suggest that you do when you encounter a problem like this is to always factor. So if you notice, the denominator is the difference of two perfect squares. So we could factor that as x minus 1 times x plus 1. And then in the numerator, we can factor this. We have to find two values that multiply to plus 3 add up to negative 4. Well, the factors of 3 are 1 and 3 and negative 1 and negative 3. So clearly it will be negative 3, negative 1. You multiply them, you get plus 3. You add them, you get negative 4. And so long as x is not equal to 1, we can cancel. Now, how do we know that x is not equal to 1? Well, we just said that we are not considering x equals 1 because it makes the denominator equal to 0. So it's not part of our domain of our function. And we are only picking values very close to x equals 1. So if we say that x is not equal to 1, then we could cancel. And now we're left with the limit as x goes to 1 of x minus 3 over x plus 1. And now I can actually simply plug in. So I could use the plug-in method. So I'm going to have 1 minus 3, 1 plus 1, which equals negative 2 over 2, which equals negative 1. So this means that the limit as x goes to 1 of f of x equals negative 1. Now, for the second problem, we're asked to find the limit as x goes to minus 1 from the left of f of x. Now, we just showed that this is the same thing as x minus 3 and x plus 1. We got that from this step right here when we factor. So we can use this again. We can actually use this again and try to see what happens when we plug in negative 1. Well, if we plug in negative 1, again, we're going to have undefined. We cannot have this. But using the same methods as we've been dealing with today, if you begin to plug in values very close to 1 from the left side, you're going to get very small values, and the numerator is staying fixed. So if you were to plug in -1 in the numerator, the top is going to be going to -4. And then the bottom is going to be getting closer and closer to 0. And because we're going from the left side, this means that the denominator is also going to be negative. And negative divided by negative is positive. And by our rule, because this is getting closer and closer to 0, let's say you have something like 0.001, and these two signs are the same, this is going to tend to plus infinity. Again, the signs, when you divide negative by negative, is positive, so that's why you get the plus infinity. And if you make a table of values, or if you follow the rule that I gave you, and again, that means that if you have a over b as a fraction, and a is remaining constant, and b is going to 0, then this is infinity. So if the limit of b, if you have the limit of b going to 0 of something like this, and a staying constant, this is going to be infinity. This limit is going to be infinity. So that's what we have here. So that limit is going to be infinite for number 2 because of that. Similarly, if you were to do it from the right side, limit as x goes to -1 now from the right side of f of x, then we have a similar situation, x minus 3 on the top, x plus 1 in the bottom, the factor version. But now, instead of plugging in, well, the top is still going to be -4, because if you plug in -1 in the top, you're still going to get -4. But now in the denominator, since we're coming from the right side and not the left side, these values are going to be positive, because the closer and closer you get to -1 from the right side, you're adding 1 to all of those values, and all of those values are less than -1. This is going to remain positive. So you're going to have some positive value in the denominator, which means that negative over positive is going to be minus. And again, by this rule, it's going to be minus infinity. So the infinite limits as x goes to, so as x approaches -1 are plus minus infinity. So limit as x goes to -1, even though we were not asked to find this, does not exist. Finally, I'm just going to graph this so you can see exactly what went on in this particular function, because it may not be too easy to see. So let me graph it here. Let me call this h. So you have h of x, and that equals the function that I had was, the original function was x squared minus 4x plus 3, all divided by x squared minus 1. Okay, so this is what it looks like. Now, GeoGebra and some other graphing calculators will not show you two things. It will not really show you the vertical asymptote at -1, although here we can clearly see that from the left side we're going to plus infinity, and from the right side we're going to minus infinity. And it's also not going to show you the open hole at 1. Remember that if we have x squared minus 1, we had a hole at 1. So it's not going to show you this. We can actually graph it if we wanted to. So let's do x equals -1 here, so we could get that. And let's just very quickly just change the way it looks. Okay, so this is how it's supposed to look like. And then we have an open hole at 1. Notice that even when I try to put in the point, Maple recognizes that it's undefined, but it's still plotting it in, so it's not supposed to be in there. So when you try to put it, it's still saying that it's undefined. This is how it's supposed to look like. So clearly, as you get closer to -1 from the right, your y outputs are going to -infinity, and on this side to +infinity. And that's all I have for today. Thank you for your time.